Yeah, streaming is good. Yeah, good afternoon everyone. Today we're gonna talk about 3D model formats, and we will so know what it is exactly. So just a little announcement. Tomorrow we're gonna have the rest of the assignment 1 presentations, because 2 of you have not presented that yet, so hopefully those people will present tomorrow so that we could assess the work and also collect the data for further assessment. And also, Halvor, as far as I know from Christopher, you will present some assignment 2 stuff from the last year, right?
Yeah.
So please show up for the lab to get some inspiration, because you need to decide what are you gonna work on as an assignment 2. So it will be a nice way to get familiar with the previous year's work and get some ideas and inspiration. Yeah, that's it I wanted to tell, and let's start with the lecture then. So what we had so far, we had just some geometric primitives in C++, then transformations using some like matrix multiplications, textures, basic lighting models like Phong model, and we already got some like basic knowledge that we need to use OpenGL efficiently. But there is one big problem with the first element of this one. The thing is that in order to define the objects or even scenes, we need very high number of vertices and very high number of primitives. So imagine doing this manually. That's like a crazy amount of work and time, and it's super complicated and super confusing. And if you add these texture coordinates that need to be mapped with these special coordinates, it becomes almost impossible to handle very complex shapes manually, like just hard code it yourself. So what can be the solution? I think it's very easy to guess. So what's a shortcut to decrease this extensive amount of time and work? Yeah?
You just load in models?
Yeah.
Like using Asym for something?
Yeah. Exactly. So loading the model already ready and defined model from an external file. Yeah, another problem is that and pretty challenging one is that engine developers, game designers, and model designers are not very often the same people. So there is sometimes compatibility and understanding problem, but still this is the most efficient way to handle our models, our shapes, and not only shape, we'll see later that can be encoded lots of appearance stuff and other functionalities. But it's definitely faster and smarter and wiser decision to use the models rather than hard coding them yourself. And it's actually a separate market developed based on those stuff. Like you can, if you make a really good model, if you design something really useful, you can even sell it. So we can have a look at one of the examples. So this website. So free3d.com, this is one of the websites where you can find some interesting models. Like many of them, as you see, are completely free, so you can open them and download directly, while some of them cost some money depending on I don't know how complicated they are, how much work they need to be modeled, but there are like lots of options. If you select, for example, this one, you have the information, what kind of formats are included for this model, and like number of polygons, vertices, and all kind of parameters you might need to know. And you will simply download this one and use for your work. And to get back to the presentation, yeah, here is another also very good source. So any familiar objects, any familiar shapes that are very common, very standard in computer graphics, can you name some of those? Yeah.
The teapot on a dragon.
Yeah. Utah teapot and the Chinese dragon. Also, probably some of you know the Stanford bunny. That's also a very widely used shape and the model in computer graphics. Cornell box, that is used a lot in computer graphics to compare like different rendering techniques like ray tracing, photon mapping, and study the materials. Yeah, that's mostly that with the most. Yeah, you can have like something as simple as the cube. So if we open it, yeah, you see number of triangles, number of vertices, and it can be as simple as a cube. Sorry, yeah, just 12 triangles. And it can be as complicated as the whole scene, like this one, for example. So this has 6,700,000 triangles and 12 million, more than 12 million vertices. So pretty complicated and almost impossible, if not impossible, to handle manually. So you can use, I think all the resources are free here, but you can check those out. This is also Happy Buddha is also a very popular one. So yeah, Stanford bunny is popular because of its shape complex. It has a very bumpy and complicated surface, thin ears, that is a challenge in 3D printing. So all those shapes have the characteristics that are usually interesting for people working with either 3D printing or computer graphics. So they have a very diverse characteristics. Yeah, let's get back to the presentation. Yeah, what are the characteristics of different 3D model formats? It can be either open or proprietary. There are lots of proprietary formats. You're either binary or human readable. So the human readable ones are that you can just simply open and understand what's happening there, and they're very convenient. And we will have OBJ format that is human readable one. And there are like lots of different features like support of textures, transferring the models, supporting and including the materials, animations, collision detections, and interaction with the user. So they're like, they come with lots of different features and lots of different capabilities. So this is a long list of various formats. So actually all developers, softwares, everyone came up with their own, apparently their own format. And we got this long list of formats. So 3ds is like 3ds Studio Max format. That is a binary one. That is industry standard and pre-established standard. However, it's not very compatible. It's proprietary and not very convenient to deal with yourself and modify stuff and play with. And the blend one is Blender format that includes like textures, lighting, animation, post-processing, everything done in Blender. And it's a bit more generic than 3ds, but still limited in that terms. Yeah, DXF is AutoCAD format. What else? Yeah, MD family of the formats are from Quack game engine that's I think pretty old already. What else do we have interesting here? Yeah, more or less. That's more or less it. And here we have other ones like OBG. That is one of the widespread and established standards, and the one we are gonna deal with and like look into depth. Polygons are primarily for like 3D storing the 3D scanned objects, and it comes in both versions, like ASCII version and the binary one. But it's like the side of the polygon is a pretty small one, and it's pretty convenient in that sense. VRML, like virtual reality modeling language. So you might think that this is something new, modern, but actually this is deprecated. This was used in 90s for web, where like VR was also kind of hot topic that times, and they wanted to implement the virtual reality for web-based applications, but nowadays it's just replaced by X3D. That is the most common web standard and used for web. Yeah, and POE is POV ray tracer software, proprietary format, and so on. So we have lots of like huge palette of different formats with lots of different capabilities. But yeah, three most interesting ones we are going to look into and go into deeper details, like OBG, that is the basic change format, very common, and it's human readable and very easy to understand. X3D, a web standard, and 3ds for CAD applications. Let's start with OBG. So OBG is not a new one. It was actually created in 80th by Wavefront Technologies, that is now I think merged with Maya. And they had this software, complex software advanced visualizer. So it was not a single software, but it was a set of the different tools, like for painting, for 3D modeling, for animations and different stuff. And they had a serious need to exchange 3D models among their own tools. So they came up with OBG, then that was also adopted by other communities, and nowadays it has very good compatibility and it's very widespread. So it has ASCII format, readable, you can use comments, that makes it even more clear and understandable. The drawback is that you don't have absolute units, so you can't indicate, for example, centimeters, millimeters, or meters, so there are no absolute unit support. And yeah, it's broadly supported, lots of features, but I'm not sure exactly which softwares, but I've read that it can have incompatibility with some particular softwares for some particular features, but not for the core functionality, of course. Yeah, I think it will be the best to look into it directly and go through how it looks. Wow. It's better to here. Yeah. Let's start with the cube. So yeah, you can also open the cube, like for example, or like any shape with 3D Builder, to have a quick look in Windows machines, to have a quick look how it looks. Yeah, like this, for example, we have very simple shape. And now let's have a look how it's implemented in OBG. So it starts with commands that just like says it's made in Blender, like simple information, and then the next is material library. So this is an external file, .mtl file that includes material information. So we don't store actual material characteristics within the OBG, but we have this support MTL format that includes all appearance related stuff. And then we have like vertices that are very simple to do you see it well, or shall I zoom in a bit?
Yeah.
One more. Yeah, so we have the vertices here, X, Y, Z, very intuitive. Yeah, any guess what is VT? Yeah?
Texture coordinates, probably.
Yeah? Yeah, very good. Why do you think it's texture?
Because the elements there is vertex and VT at the end, so, and they didn't use UV, so T makes sense for texture.
Okay, and another cue that we just have 2 coordinates. Yeah, while in 3D we have like 3 coordinates for vertices. UV is usually given in UV. Yeah, and what about VN? Yeah.
Is that the normalized?
It's, yeah, normals, vertex normals. So vertices, vertex textures, and vertex normals. So very intuitive, very easy. And the good thing with OBG is that order does not matter, so you can have them in any order. Then we have this syntax, use MTL, and we indicate what material should we use. So it can be either something from the library, but it is not the case in this one, or it can be a texture or something external. And S off means like smoothing off. What smoothing does is that the surface, vertex normals are found as average through interpolation of among the normals of all faces this vertex participates. So all face has its normal, but this, when we have like very dense mesh and when we have lots of tiny triangles or other primitives, sometimes this can, so many normals can lead to unnecessary corners, unnecessary shadows. So this is a simplification. S stands for smoothing. What it does is that everything that is written below smoothing, if this is not off, we take those, for example, those primitives and just interpolate their normal. So we take, so the F stands for faces, for example, so we take the surface normals of those faces, we interpolate and get one average normal. So for many primitives we have a simple formula that gives us impression of larger face and like smoother surface. So this is for reflection and lighting, but you need to use this carefully, because if you smooth it a lot, you will end up with very low pol image. So we can have a look. Oh, come on. Yeah, something low poly. So actually what happens here is that we have just one average normal available for possibly many little triangles here, and the appearance looks kind of like very low definition mesh. Yeah, so this is one of the functionalities, and let's get back to this. And yeah, those are the faces, as I already mentioned. And here we have triangles, but technically there can be any number of vertices, so any type of polygon. If we have like 4 or 5 vertices, so here what we have is that one vertex, second vertex, and third vertex, and here we have fifth vertex, first texture coordinate, and first normal. And then we have the second vertex of the triangle and the third vertex, and that's how we define the triangle. So this is one triangle, and within this triangle we have like these triplets of 3 points, and within this one we have actual vertex index, texture, and normal. So texture and normal are optional, so you might have no texture, or you can leave normal also like blank, and it will come up with it automatically considering your 3 coordinates, but it's sometimes good to have more control on your shape and on your lighting. So I think this is very simple and straightforward. Any questions so far on this? So everyone gets how the triangles are defined, right? 3 vertices, and within each vertex, number of vertex, number of texture. Like it's actually these were like 5th vertex would be. So we start counting from 1 here. So it's 5th vertex, first texture, and first normal. So that's very simple and straightforward. Yeah, and here we have other elements of syntax, like vertex can be like indicated at x, y, z coordinates. Like texture is UV, and homogeneous coordinates optionally, like normals. And the elements, in this case we had just faces, but also we can have points or lines or curves and surfaces, and this is just a regular expression of the fact that we can have we need to have the vertex, and we can have optionally texture and or no, I will show you what are the possible, yeah, those are the possible face syntaxes, either only vertex, or vertex and normal without any texture, or vertex, texture, and normal. And the regular expression, so I just used color coding to make it easier to read. So what we have here is that we are looking for, is anyone familiar with regular expression language? So yeah, like the first one is vertex number, so we're looking within this range with at least 1 match, and then we have slash that divides vertex from texture, and then we have the same kind of search for texture, but when we have the question mark, it means that there is either 1 match or 0 match, so it's kind of binary. We can have this, or we can also skip it. And this, the same we have for normals, and then we either can have texture and normal on or off, kind of, and then we have like all the 3 elements match. So it's kind of just expression of this syntax. So either only vertex, or all of them, or vertex, texture off, and normal on. But it's pretty not very intuitive at first glance. Yeah, then we have grouping features, like we can use grouping different primitives to have. I will see an example why is it useful to have, for example, within a scene, a table as a separate group, or like table as a separate object. So both are possible in this case. We can have smoothing that we already mentioned and merging of different groups. And finally, render attributes, so appearance related stuff, either using the material library, defining the material library file itself, and different levels of details and shadow objects that we're not going into details, but let's have a look at another shape that makes easier to understand this. Oh yeah, by the way, there is OBG official specification where you can see all the syntax and all the features supported with the OBG, like elements, freeform curves, and different grouping, rendering, and visual appearance attributes, and everything that you might need to work with the OBG file. So the specification file is kind of good dictionary for finding the proper syntax. But right now we need another, let's have a look at Cessna. Yeah, so we have library file defined, and then we group those vertices together so that we have lots of vertices. For example, let's find, so we have a group called nose that uses a black appearance parameter from the library. So it's some material properties encoded, and it applies these appearance properties to this group of the faces. And why we need this is that it's very flexible. So instead of dealing with one huge, very cumbersome model, we can split into smaller groups to apply different materials, different operations, and we will see now a good example of this. Well, where is just this? Yeah. So this is a very good 3D viewer. The only drawback is that it does not allow uploading MTL files. So the only thing we can upload is just shape or the model, but still it gives us opportunity to work with shapes very easily. Okay, sorry. Let's take Cessna. Yeah, and we have this beautiful airplane model. So this airplane is actually this one, this file. And here we have it even says which files are missing. We don't have here the material library. It understands that it's missing, vertex count, triangle count. In this case, we have a default neutral gray material, and separate groups of the meshes. And with this one, you can see how this complex shape is split into smaller pieces to handle it more easily. For example, we have glass, and for if this is something like metallic, we apply different material properties to glass in rendering, so it's very easy to handle all those vertices and primitives together. We had nose in the code. Yeah, so it's just like front, probably different color than the rest of the fuselage. Yeah, different parts. So did you get the idea why I need to group the elements in OBJ? What is the advantage of it? So it's very flexible. It gives us better control of the model. That's the primary reason. Yeah. Yeah, that's more or less it. We have talked about low poly. Yeah, this is just an example from OBJ, but I think the content itself is more or less clear. But now, very important question: how are we going to use all this information? It's easy to open in some like 3D viewer or inspector, but how are we gonna use this one in OpenGL? What do we need for that, or how should we import that? Any idea? Or yeah?
You can use the specification and write your own loader, or use the library, I guess, to load it. But you want to load the vertices into that vertex buffer and use the faces to index into that, I guess.
Yeah. So yeah, that's that's actually true. We need a dedicated object loader. Either we can code it ourselves, or there are like some module loaders available already that will load those ones. But how do you see the workflow itself? Like, what should be the output of the loader? What do we need to have to continue working in OpenGL? So you have OBJ file, you have some loader function. What should be the output? Yeah?
An array of vertices?
Yeah, that's one thing. And also, anyone else? Yeah, the same thing that we had there, like array of vertices, array for texture coordinates, array for normals, and also the indices to get the idea how to compose them. So here is the pseudocodes, how it's done. Actually, exactly, we have some OBJ file, and our outputs are 4 vectors, 3D coordinates for vertices, UV vector for like texture 2D coordinates, normals, and indices. So we read the file line by line, and if we match, if we see it's a vertex line, then we parse it as vertex and add to some like temporary variable for vertex. The same is done for UV and normals. So we just read line by line, and if it's vertex, take that vertex and you put add to some temporary array. And finally, when we reach that phase, we use the indices. We have used for phase definition to build this packed vertex that is actually a single array that includes vertex, texture, and normal. And we add it to some dictionary, and we have index set to index array. And finally, what we do is that we take this packed vertex that includes actually a triplet array vertex texture and the normal. We find it in the dictionary where we defined all those combinations and take vertex and write it, add it to the final V vector and take texture to add to the UV vector and take normals out of this triplet and add it separately to the normals, and the indices that we read from faces are written here, and finally we get 4 vectors for vertices, UV, and indices. So the reason why I needed to build these packed vertices and read faces separately is to have the okay, we could directly read vertices, but we need the proper indices in the right order to compose them in the right way. I think it would be easier if I show this in C++. Actually, I had some bugs that didn't allow me to run it, but I think it's still good, still good to have a look, just to have an idea how it would look. And I think then you can play with it and you can look into it yourself, but like the general idea of and principle of this. So we have some function get module. We have character of the path of the OBJ file, and then we have 3 vector variables, vec3 for vertices and normals, and vec2 for textures, and then we allocate some variables to store intermediary data. So this is temporary vector to store the values. We will see that. So and then the idea is that okay, here it's just to if the file is not found, just to give the proper message, and then we run, well, that's not the best and smartest way to do, but still we break out when we are at the end of the document. So we run the infinite loop, we create some symbol, and then we start scanning line by line. So if we reach end of file, so if we have scanned all the lines, maybe I'd better zoom in a bit. Yeah, I think this is better. So if we reach end of file, we just break out and stop execution. Otherwise, we start line by line from this OBJ and try to match this first character of the line with the V. So if this is a vertex defining line, we define a vec3 vertex and then read it according to this pattern. So we have 3 floats, x, y, z, and end of line, and we extract them to vertex x, the x coordinate, y coordinate, z coordinate, and by pushback we simply add this at the end of temp vertex array. And this way we, in temp vertex, save all x, y, z coordinates of the vertices. And similarly, actually, if it's not V, then we compare against VT. So if it's texture line, exactly the same logic. It should be, I think, vec2, yeah. Whatever right now. Yeah, and we compare by this pattern, so 2 floating points, U and V coordinates. We extract them, like save them, and add at the end of the temp UV array. And if it's neither VT, then we check for VN. If it's normal, and exactly the same procedure. And finally, when we reach faces, we start extracting the indices. So you remember, so what we were doing here is that, I think it's easier for a cube. So check this character. If it's V, we take those three and write into the corresponding array for vertices. Check if it's VT, we write those ones to texture array and so on. And when we reach the face, we start scanning those indices 1, 2, 3, 1, 2, 3, 1, 2, 3. So it should be 9 floating points in total. So we have, it's actually, yeah, decimal. So we scan for this pattern, and then we have to write them out actually, like vertex index first, second, third, like UV index first, second, third. So don't mess it up. Even though we have 2 coordinates for UV, we have 3 different UV for 3 different vertices of the triangle. That's why we have 0, 1, and 2. And then we have the same for normals. So if the number of those in this pattern is not equal to 9, we have wrong format. Probably we have just vertices specified, so we have the message, but you can code like for that case, like simply with different pattern. And finally what we do is that we store all those vertices. The vertices read from, so they're the like indices from read from here. So this one, this one, this one, and so on. And we save it. And what we do finally is that we are running the loop to extract like corresponding index values, and then take this index, corresponding index, and look into temp vert where we saved actual vertex coordinates and write into vertex. So here we have the indices that were defined in the faces, and that we use that indices to pick up vertex coordinates or UV coordinates from this long array that includes all of them. Oops, sorry. And finally, we simply pick them up and write in final vertices, final UVs, and final norms in the right order, considering those indices. And yeah, one quick question: why do we need -1 here? So we have vertex indices, and we have to reach it in this array. So why do we subtract 1? Yeah?
Is it because OBJ starts with a 1 index?
Yeah, exactly. So C++ starts from 0, while OBJ starts counting from 1. So if the index is 1, it's actually zeros coordinate in C++. So just kind of little incompatibility to correct for. And yeah, finally we have those final vertices, final UVS, and final norms to use further in the rendering pipeline, and we close the file. So is it more or less clear? So this is C++ implementation that has apparently some syntax errors and doesn't run, but like I just wanted to show you the idea. So this is actually, let me again open. This is actually this. So is it clear how do we load and how a sample loader might look? So we read the vertices, keep it in an array, then we pick up these vertices in the proper order, considering the faces, and then we use these indices to read the vertices and write in the final files, final variables arrays, or like any data structure. So I hope you will manage to play with this a bit yourself. And there are also like other object loaders available. Sure. Yeah, just finish with this one and continue with material after the break. So here, again, what we said that object contains all elements related to actual object, like vertices, faces, any kind of primitives. For example, here, face is composed of 4 vertices, so we have a polygon with 4 sides, and group contains all geometry associated with this group. So when we group, like let's call it exhausts, and group them on, this is kind of part of that airplane, and we have some faces that are considered together as a single entity. And then we can apply different materials, like reading from the library, and we will see this after the break. Smoothing group that we have already seen, that we just interpolate the surface normal to have smoothing representation of maybe bumpy and cornery surface. And we will continue with materials and look into material files. Yeah, any questions so far? Does this silence mean that you understood nothing, or you understood everything?
It's good. Getting the idea at least.
Okay. Yeah, that's the key purpose of the lectures, to get the idea, because we can't like cover all tiny details, and I know at first glance this is super complicated, looks super complicated, but if you get the idea and the principles, then it will be easier for you to implement in practice. So I'm happy if it's okay in that sense. All right, then let's continue in 10, maximum 12 minutes.